Hey guys, welcome back. Hey, in our last video we talked about reaction rates, how we could determine the average reaction rate over the course of a reaction based on the changes in concentration of a reactant or a product over time, and that gives you your average reaction rate. We also talked about collision theory, how in this reaction when these molecules are coming together, they first have to collide in order to react, and they also have to have the right orientation to react, and they have to have enough energy. When they come together, they form that activated complex to give us the reaction. Now today we're going to talk about factors that can change the rate of reaction. So stick around. For our first factor today, we need to talk about the nature of the reactants. Now, I have two beakers here, as you can see. In both of them, the liquid is silver nitrate. It's a silver nitrate solution, and you can see over here we have a zinc strip, and over here we have a copper strip. Now, whereas both of these are reacting with the silver nitrate, you can see that the zinc has reacted a whole lot more in the same amount of time. See all the black on the zinc there and all the particulate matter in the solution? All this shows us that zinc reacts more quickly with this silver nitrate solution than the copper does. That's because the zinc metal is more reactive than the copper metal is. So if something is more reactive, it's going to have a greater effect on the rate of reaction. So I have two flasks here. In one flask I have concentrated hydrochloric acid. In the other flask I have a more dilute form of hydrochloric acid. Now in both I'm going to put 4 zinc pellets. You see the zinc in there? 4 zinc pellets. I've already put 4 in here, and now I'm going to put 4 in the concentrated flask. Here we go. Wow. Notice the difference there. Notice how much more bubbling is taking place over here. How much more reaction is taking place. That's because the more concentrated the reactants are, the higher the reaction rate. If you have greater concentration, it means you have more particles in there that are available to collide. And when you have more collisions, you have more reaction. So a faster, a greater reaction rate. Now in these two flasks I have the same amount of hydrochloric acid, but in the one I put, again, these zinc pellets. On the one on the right, though, I put zinc powder. Notice how much more the zinc powder is really reacting. That's because surface area is directly related to reaction rate. In other words, the more surface area you have, the more opportunities you have for collisions to take place between reactants. And when that's the case, you have a greater reaction rate. So if you increase the surface area, you will increase the reaction rate. So far we've seen that the nature of the reactants affects the reaction rate, the concentration of the reactants affects the reaction rate, and the surface area affects the rate of reaction. For the last one, I want to show one more thing. In both of these flasks, I've placed hydrochloric acid. Now, I've also got in these graduated cylinders equal amounts of sodium thiosulfate. And what I'm going to do is I'm going to pour the sodium thiosulfate into these flasks, and we're going to wait to see if a reaction occurs. Wow, so notice that the reaction has already occurred in this flask over here, and we're just now starting to see some cloudiness to develop in this other flask over here. So notice how much faster it did over here. Why is that? Well, obviously I have this one on a hot plate. Obviously I've increased the temperature. Think about it kinetically for a second. All those particles in there, when they have greater temperature, they have greater kinetic energy. And that means they're moving around much, much faster than they are at room temperature. When they're moving around a lot faster, it means they have greater opportunities for collisions. And when they have greater opportunities for collisions, that means there's greater opportunities for reaction. When you increase the temperature, it will increase the reaction rate. So, our factors affecting reaction rates. 1, the nature of the reactants. 2, the concentration. How many particles are in there to begin with? 3, surface area. How many places are there for these particles to collide with each other? 4, temperature. Is there more kinetic energy that allows them to have the necessary energy? And then a 5th one, the catalyst. A catalyst is a substance that assists in the chemical reaction that increases the rate of the reaction without itself being changed in the process. Pretty cool. So if we're using one of these energy diagrams, and if these are our reactants right here, a catalyst would cut down on the amount of activation energy that's needed. So instead of having all of this activation energy, you'd only have this amount of activation energy. So that's what a catalyst does to increase the reaction rate. It lowers the activation energy. On the other hand, an inhibitor is something that increases the amount of activation energy necessary for a reaction to take place. We use inhibitors all the time. We use them in food especially. You ever heard of a preservative? A preservative is a type of inhibitor that keeps that oxidation process, that rotting process from taking place in the food that you eat. And so, therefore, it inhibits that process. Hey, so that's it for today. All we did was talk about the factors affecting reaction rates, and we've done it. It's a short one. You like those, I know. Hey, only one thing I want you to do for me, and that is to have a great evening. No homework tonight, okay, guys? Have a good one, and until I see you next time, God bless.